Welcome back to the ChemDoctor, and this is going to be the fourth video in the series on chemical kinetics. And what I want to do with this is introduce the concept of the rate law, and in particular what we call the differential rate law. So basically, to introduce this concept, we're going to consider a chemical reaction where we have a single reactant that's being converted into a product. All right, and if we were going to follow the kinetics of this reaction, we would start out by following an initial concentration of what I'm going to call A here, which could be 1 molar, for example, and then we would have some kind of a time frame that we'd be following the conversion of this material into its product that I'm calling B. And if we plotted this data, this is what it would look like. We would have concentration of A on the vertical axis. We would have the time frame down here on the horizontal, and you would expect, let's see, we're going to be starting here at about 1 molar is what I was saying, and then you'd expect the concentration of A to decrease with time like this, and eventually the curve as we reach the end of the reaction would become asymptotic, or it would flatten out when we reach the equilibrium point of the reaction. Now, in kinetics, we're studying the rate of reaction as close to time zero as possible, and we call this initial time kinetics. All right, and what that means in English, let me just write this up here, initial time kinetics. All right, what this means in English is that we're going to collect and analyze data that's very close to t equals 0. So if I put 0 here, we're going to be looking at what's going on with the rate of this reaction as we approach 0, and what this means is that we will be looking at a tangent to the line, which is going to be in this region here. All right, again, really close to 0. So if I'm going to write the rate expression for this reaction, or what we're going to call a rate law, this is what it's going to look like. So we're going to have negative change in concentration of A. Again, the negative sign is just to indicate that the concentration of A is disappearing with time. The concentration of B, on the other hand, is going to be increasing. If we were to put B on this graph over here, you would see it going up like this. Right? It would be a reflection of A. Since my coefficients here are 1 to 1, B literally would be a reflection of the curve for A in this case, because the coefficients are equal. The rate expression for this will be minus change in A over change in time, and then we're going to set this equal, well, to the rate. And then this is also going to be equal to a new quantity, which we're going to call the rate law. And the rate law will be a rate constant times the concentration of A raised to an exponent that I'm just going to call x here. All right? And this new expression is what we call a differential rate law. And what it does is, let me just write this down, so differential rate law, and what this does is it relates the concentration to rate. So it tells us how the rate of the reaction is being affected by the concentration of A. So let's go ahead and put this in here. This tells us how the rate is affected by the concentration of the reactant. So by the concentration of A. All right, let's just say it that way. Now, let's define the things that are in it. So I'm going to rewrite the expression here. We have rate is equal to rate constant times concentration of A raised to the x power. All right, so the K value here, this is what we call the rate constant, and we're really going to talk about the specifics of this later on. It's a constant, which means that if we're at a fixed temperature, this value is not going to be changing. And I mentioned in previous videos, this is going to have, there are three main components. It's going to have in it the frequency of collision, the orientation of the collisions, and the energy of initiation of the reaction. Those three things are wrapped into this constant. The A, of course, is the basically it's the initial concentration of A, and then we have this thing called X, which is the order of reaction. Alright, so order of reaction is an exponent that is defined experimentally, so you can't guess this value, and it does not come from the coefficients of the balanced equation. So the exponent is defined experimentally only. We have to get it from our data, and I'll be taking us through some videos that show us how we do that. First off, though, I want to describe what this thing is. So this value is going to tell us how the rate is affected by concentration changes. All right. So the differential rate law shows us how the rate of a reaction is going to be affected by changes in concentration. So what are the values of X? Now, here's what the viewer needs to realize. X can be a lot of different values. It can be even fractional. But in a university level class and in advanced placement chemistry, usually this value, to keep things simple, is going to be one of three values. All right, and I'll lay that out. X can be 0, and this would be what we call a zero order reaction. X can be equal to 1, right, and we would call this a first order reaction. And X can be equal to 2, which we would call a second order reaction. Second order. Alright, so let's take each one of these individually. So if I write the expression where X is equal to 0, or a zero order reaction, this is what the rate law would look like. And you can see that if I go ahead and put the exponent in as 0, alright, so mathematically what happens when we raise anything to the 0 power, and the bottom line with that is that anything raised to the 0 power is equal to 1. So you can see what happens with a zero order reaction. The rate literally is equal to the rate constant, because this expression right here is reduced to 1. So if we were to plot, I'm going to squeeze this in up here. If I was to plot the rate of the reaction versus concentration for a zero order reaction, what's going to happen is you're just going to see a horizontal line here. Alright, and the reason for that is because you can change the concentration of A all you want for a zero order reaction, and nothing's going to happen to the rate. Now, I will probably deal with this later in a separate video, but usually these are catalyzed reaction, or reactions that have catalysts in them. And the reason for that is because in a catalyzed reaction, literally the rate of the reaction is going to be dependent on the catalyst, and it's going to be independent of the concentration of the reactant that's in there. Alright, now for now I'm going to leave this behind, and we're going to move on to a first order reaction. So we'll do the same thing here. We'll write the expression where rate is going to be equal to the rate law, so it'll be rate the rate constant times concentration of A, and now this is going to be raised to the first power. Now if we ask the question, okay, what does this mean exactly? Since the concentration of A is raised to the first power, what this means is that for a first order reaction, the rate of the reaction is directly proportional to concentration. Alright, directly proportional to concentration. So rate directly proportional to concentration. Alright, now let's play around with this a little bit so you can see what I'm talking about. All right, remember that the rate constant is a constant, so I'm essentially going to ignore that here. And let's say that we have a rate of reaction where the concentration is equal to 1, so I'm going to go ahead and put that in. And so you can see that the rate itself is going to equal 1 times whatever value the rate constant is. All right, now let's say we run another experiment, except we double the concentration of A. So now when I rewrite this expression, you'll see that the new rate is going to be equal to K times 2. So the effect on rate when we doubled the concentration was to double the rate. Similarly, if we were to cut the rate or cut the concentration in half, so I plug in 1/2 for concentration, and you can see what's going to happen to the rate. The rate's going to be cut in half. So the bottom line with a first order reaction is whatever you do to the concentration, there will be a similar effect to the rate. So if we double concentration, you double the rate. If we cut the concentration of the reactant in half, then you expect the rate to also be cut in half. If we triple the concentration of the reactant, then you're going to see the rate tripled. All right, now let's take a look at a second order reaction, and if I write the expression for that, the rate's going to be equal to, again, the rate constant times A, but now that exponent is a 2. So you can see what's going to happen here is that whatever we do to the concentration of A, the rate is going to be affected by the square of whatever we do to that concentration. So the rate is proportional to the square of concentration. All right, so let's play around with that a little bit. Let's say that we take our concentration of A and we double it. So I'll put a 2 in here, and then the order of the reaction is 2, and you can see what happens here. The rate is essentially equal to K times 4. So the rate in this case was actually quadrupled, right? We doubled the concentration of A, and you see that the rate is quadrupled. So in this kind of rate law, where the order of the reaction is 2, when we manipulate the concentration of the reactant, there's a far more dramatic effect on the rate of the reaction. All right, and with that, I'm going to go ahead and close.